something that came out in our research is that you've spoken in the past about how terms, neuroscience terms related to these temporal patterns, like neural oscillations,
Yeah.
how that sounds like a technical term. It sounds like that's describing something concrete. But in fact, when you try to define it concretely, there's little there.
Yeah, I would agree with that.
Yeah, I mean,
And
yeah.
yeah, so the reason why we take the approach in my lab of trying to stick as close to the data as possible
Mhm.
is because we strongly believe that the misapplication of analytical tools to our data have led us astray, led us down wrong paths. So, concrete example with the neural oscillations. People probably have heard of brain waves and things like this. And, if you're a little bit more, you've taken an intro level psychology class or something like that, you'll hear about like delta waves and alpha waves in sleep. The EEG, the electroencephalography, the non invasive recordings of brain activity that we can use by placing electrodes on the scalp that is just about 100 years old now. You can see these really clear patterns in the voltage changes in the EEG as like people are waking up and falling asleep. And this is partly used to try and classify different sleep stages, REM, non-REM, all that kind of stuff. And when you look at some of these data in the EEG, when the clinicians who were first doing this back in the 1930s, 40s, and 50s were looking at these signals, they would use language like these look like waves. And the very first rhythm, the very first signal ever recorded in EEG back in 1920, published in 1929 by Hans Berger, who invented EEG, incidentally, while trying to prove that psychic phenomena were real.
I
But
didn't
when
know
he
that.
he he invented EEG, he discovered what was referred to for a long time as the Berger rhythm, named after him, which we now refer to as alpha waves, which are these 10 hertz ish oscillations in the visual cortex. Really clear, prominent, true oscillations in the data. And once digital signal processing came about, right, EEG used to be just scribbles on paper, right? The voltage signals from the EEG electrodes on the skull in the pre-digital era were transduced using little piezoelectric motors into wiggles in a motor, and that motor is connected to pens, and those pens would draw on an unspooling piece of paper that would unspool at a constant rate that allowed you to trace the actual EEG signals. In the post-digital era, people realized that one way of analyzing these like brain rhythms, these alpha waves, for example, in the visual cortex, instead of having to count the number of times the wave crossed the zero voltage mark on a piece of paper, you can instead use something called the Fourier transform, which is, in my opinion, one of the most brilliant insights in the history of mathematics, which is that any time varying signal can be perfectly mathematically represented as a sum of sinusoids described by their frequency and their amplitude, and also their starting phase. Widely used for data compression and all this kind of stuff.
You joked earlier in the episode that this is what we were going to get into.
Yeah, I told you I was going to get into the Fourier transform. We can dive into it. No, I'm not going to go any deeper than that. I promise. I will leave it at the surface level. And so people realize that you can use this to look at your signals. Specifically, you could like filter your data at 10 hertz around the alpha rhythm and isolate the alpha rhythm so you can more easily analyze it relative to all of the noisy background signals of the EEG. That became the dominant form of analyzing EEG data then, was filtering the data in these frequency bands that that you want to look at: alpha, theta, delta. Well, let's go in order: delta, theta, alpha, beta, gamma, in the order of frequencies. These are the dominant rhythms of the EEG. But the math is such that if you take any signal, even a purely noisy signal, like Gaussian distributed white noise, where by definition every data point is independent from the next, and you filter it in a frequency band, it sure as hell looks like an oscillation. And so we've become convinced that most people in the field started by trying to come up with simpler ways of analyzing data than counting the number of zero crossings, started using very reasonable mathematical tools like the Fourier transform, and then forgot that the Fourier transform is a mathematical operation that will always return what you ask of it, and just started looking at their data only through the lens of these oscillations. And what's funny is we've known that this is wrong since the 1940s. There's a very famous paper charting the sea of brainwaves published in Science by a neurosurgeon Jasper in 1948, where he coined what's called the Fourier fallacy, which is it is a fallacy to presume that because your signal can be decomposed into sinusoids using the Fourier transform, that your signal is composed of sinusoids, of oscillators. It doesn't have to be. The math is just doing what you ask of it. And so when we look at the raw data coming off of most neural signals, there aren't oscillations. There aren't these rhythmic signals. More often than not, it just looks like noise. But there's many different forms of noise. And so we've actually sort of spearheaded this sort of new direction in the field of looking at this, what we've referred to as aperiodic activity. So you have white noise, which is purely like, static kind of every data point is independent from the next. But then you can have like brown noise and pink noise, which are more like random walks, where it's still random, but there are correlations in the structure so that one data point isn't totally independent from the next. It's still moving randomly, but there are correlation structures in those. And neural data actually has more correlation structure in it. And different brain regions look more like white noise, and other ones have more correlation structure. And so our spectral parameterization Python package was developed to quantify this aperiodic signal, which has traditionally been just averaged out as noise, and saying, this, we know where this signal comes from physiologically. It's not just noise. And in fact, it's time varying in interesting ways. And that has just like exploded. The paper that we published for this Python package, introducing this sort of concept and applying it to neural data, we published in 2020 in Nature Neuroscience. It's just parameterizing neural power spectra is the name of the paper. And that's been cited like 1,500 times or something at this point. And like I said, by fields like very wide ranging, right?
I just opened up Google Scholar to your page, and that is by far your most popular paper, and it's only a couple of years old.
Yeah. And it's really, it's funny that I gave talks at this like Society for Neuroscience conference 10 years ago, talking about this issue, this problem of like, we can't just presume that this is noise, and we can't also presume that everything is an oscillation. We have to really be thinking more carefully about our data. And people would just be like, either, yeah, kid, you're wrong, shut up, or okay, so what? And so this is why my lab has become very big proponent of writing software that is easy and intuitive to use and well tested on many different kinds of data. Because if you offer people an easy way to analyze their data in new ways, that then opens up new opportunities for them to find new discoveries in existing data, publish new papers, which is what scientists really like care about, because that helps them get new funding, and it opens up new research opportunities and so on. And so we sort of took this approach of, all right, nobody's actually listening to our theoretical arguments, so let's write good code to force people to analyze the data in ways that we think are better. And we're not saying that our tools are the correct way, and by no means. In fact, we actually sometimes say, there are better tools that we should be using. And we try and fold those into the greater sort of neural data analysis ecosystem. And so we're not trying to build, we're not trying to say, we're trying to build, but we're not there yet. We're not trying to say that our approaches are the correct end point. They're just the next step in how we should be thinking about analyzing data. And I truly, genuinely hope that people take the open source code that we've written and make it better, like do it better, show that we're wrong in some ways. There's sort of a joke in my lab that like anytime somebody publishes a paper that seems to like overturn or pushes against something that we say, I try and hire that person because I'm like, oh, all right, I like this. Like somebody's really pushing our ideas and trying to make it better. Like let's bring them into the fold. I want to hire them.